So we're gonna do most of we're gonna do so we'll do all of chapter 2, 1 through 2, 3 today. So let's see here. These three sections that probably and here. 2 more I'll probably do on my video, right? And also showing you how some other things on Excel in the video, right? And then chapter 3 you can probably start using that, right? So we're not going to do all of this stuff. We're not doing this for 2, 4, but that doesn't mean you're not going to learn it. The stuff's also covered in chapter 10, 9, something, right? So I just thought let's not try to. It's useful. I think they put that in this section for people who don't get to that section of the book because that section is very useful and you can do it now, but it wouldn't make a ton of sense yet because you don't have some of the background to completely understand it. So we're basically going to talk about frequency distributions and histograms, and then we'll talk a little bit about how some different sort of ways to this data that can be enlightening and that can be deceiving. All right, so for this first section, we're going to create a frequency distribution for a data set. We're going to know what these terms mean and identify them for a specific distribution, right? And we'll use relative frequency and we'll use a cumulative frequency distribution. I forgot to write down that. Oh. Anyone else going to get into frequency going around making sure that everyone's on it, all right? So, anybody go to McDonald's recently? Drive-in? Yeah. Okay. How long did you go to the drive-in or did you go inside? Yeah. All right. So let's like that, but how long did you wait for you? Yeah. For how long? Yeah. 10 minutes. Okay. Longer time. Yeah. Okay. So I'm not sure. I guess I use fast drive. So this data is supposed to be how long it takes you to get your food at the McDonald's drive-in, right? Now these are in seconds, not minutes. Don't worry about that, right? Now, can you tell me much about? Is there an easy way to describe the data when it's streaming? Not really. You can get some ideas, right? You can see that it's a pretty long time to wait, but you can't really get much of a shot. You just have data that's now, right? This is the raw data. They literally wrote it down and the card taking the raw data. So you can't really get a sense of it unless you display it appropriately. And the first way to and this data is let's think about our categories. This ordinal, nominal, interval, or ratio data. I hear ratio. Does anyone second ratio? One think it's interval. Ratio has a natural 0 point. So does this have a natural 0 point or is the 0 point arbitrary? It's social convention. It's not arbitrary because the 0 waiting time is not waiting. So this is ratio data, right? Anytime you have a data set that is not nominal, right? That is numerical, you can't use a frequency distribution, right? Maybe ordinal would be tough. So interval, ratio or interval, you can use a frequency distribution. So what is a frequency distribution? Well, it's a table and it summarizes the data, right? It shows you the distribution, and we'll talk about what that means. It's hard to define distribution, right? And you are partitioned into several classes based on numerical values, right? So easier to see when you okay. So partition means to divide, right? So if I put everybody So this class are taken in three rows. Everyone in one of the three rows, don't with them, right? And three rows make up, right? So think about a partition. So here's the data, right? So here's how you make a frequency distribution. It helps you see going on, right? Let's look at the categories. So 11 people waited from 75 seconds to 124 seconds, right? 20 more waited from 125 to 174 seconds, right? So these are the categories. So these different things right here, 1, 2, 3, 4, 5, these are called classes, right? Here we have 5 classes. The number of classes is somewhat arbitrary. I could have divided it into 10 classes, 6 classes, 3 classes, right? You can divide it into however many classes you want, just some are more useful than others. All right. You notice anything else about these classes? Notice that they're kind of equally spaced, right? Each of the classes is about 50 seconds wide. Does everyone see that? Does everyone understand how they made this table? Is there any? Okay. So let's just give you, this isn't too hard. Let's just give you some terminology. So lower class limits are the smallest number that belongs to each class, right? So for example, this first class, the lower class limit would be 75. The upper class limit is the largest number that can belong to each of the different classes. So for this third class, this is the upper boundary. Or upper class limit, sorry. And then the class boundaries are numbers that would separate the class. So what does that mean? So you're not really using it because they're rounding to seconds, right? But the number that would be 124.5. That's exactly between 124, where the first class ends, and between where the second class begins. So that's considered a class boundary because it partitions the two classes. Class midpoint is the number in the center of each class, right? To find the middle value of two numbers, you add them together, you divide by 2, right? Because middle and average, same thing. The width is roughly how wide the class is, but notice that they call it the difference between two consecutive lower class limits. That distinction is going to be important in a second. I will show you what these are with this example, but are there any questions about what any of these words mean? If you're not quite sure, we will see an example, so that should help. All right, so let's look at the data. So let's start with the lower class limits. There are 5 classes. Each one will have a lower class limit. Of the first class, the lower class limit is, everybody? 75, right? And then the other 4 are, everybody? 5 and 275. Okay. The upper class limits are the second numbers. So the first one would be, you can kind of see a relationship, right? This is 1 less than the, right? If you go diagonally across. Might seem like it's kind of kid stuff, but it is important that we just use terminology to be specific, right? Class boundaries separate the class numbers. What would the first class boundary be? So, well, let's start to the left here. It would be that one. The first one's a little weird, 74.5. What would the second one be? Everybody, the second one would be Yeah, only a couple people are saying it, so I'm trying to see them. Yeah, just notice 124.5 separates 124 and 125. Next ones are easy. It's 174.5. Class points are the numbers that are at the center of each class. So we can, those you might want to calculate numerically. So you do 75 plus 124 over 2. So that is 199 over 2, which is 99.5. Next one you would do, all right, 125 plus 174. That is 299 over 2, which is 149.5. Perhaps you can start seeing the pattern. What would the next one be? Next class midpoint would be the center of the third class, and that would be, yeah, notice it's a difference of 50, right? And so on and so forth, right? Notice that is the class width, right? That's why the midpoints are that spread apart. The class width here is 50, but notice how you have to calculate it. This is the tricky part, and this is why there's a caution. It's the difference between two consecutive lower class limits. So let's say we take these two. Here's one lower class limit. Here's the other one. So it'd be 225 minus 175, which is 50. A mistake that a lot of students might make is to look at it within a single class. And do 124 minus 75. That will not give you 50, but instead will give you 49, right? Because of the fact that you don't want to be ambiguous about which class the value of 125 comes in. You don't want to say that 75 and 125, and then can start with 125. Notice the class limit is 50, right? Like these midpoints are 50 apart, these lower class limits are 50 apart. Like you subtract by just looking at a single class, you can get 49. About why. Here's a diagram that they kind of made from this just to show you. These are the class units. Upper, right, now upper class limits, lower class limits, right, then the class boundaries. Now notice these are measured like here in a second, so they don't have to worry about 25. Then you're taking a second, you can take it from 75 to 120 or 90, whatever you need to make it okay. It all works out. So, right, you know it's 0.5. There are no data values that actually fall in here because of the way it's measured. Okay, questions so far? Right, not thrilling. So this is the part that's a little bit trickier. Where do I want to look? Uh, Other than the fact that the data is out of order, if I had left this part of your column blank, you could have easily filled this out, right? By just counting and crossing off. The harder part is actually filling out this column, right? Because, right, if you have a frequency table, you're not just going to be given a table. You have to decide what type of table you want to make, right? So here's how you have to decide that. First, you want to choose the number of classes, right? And there's an argument. Look at the logarithms that use that. Right? You want to be between 5 and 20, right? If that's bigger than 5, your data distribution where you don't have enough data, right? If you have more than 20, or it might be more than 10 person. You don't have, like, if the number of classes you're supposed to have in your data, right? Many of your classes will be empty, right? Classes are all tiny, right? If I made them all 10, right? Well, most of them would have been empty, right? So you don't want to make there be too many classes. The class width is going to be approximately equal, right? Your minimum data value, the maximum data value minus the minimum data value, divided by the 1.5. The reason why they set class width is because it's approximately because you can make it a nice round number, right? Long as all your data is. Now it says approximately, but I would actually say, notice what this formula is doing. It's looking at our range of data, right? It's telling if that difference is 180. It's telling you, okay, the difference between the smallest and the lowest piece of data is 180. You want to easily divide that into 5 classes, you divide by 5, right? Now, if you round down, you won't make it from your minimum to the maximum. Everyone's trying to follow what I'm saying there. Round down. Like if this was 31 and I rounded down to 30, I add 30 5 times, I would end up missing my largest data value by 5. And you want all of your data to be. So while this is an approximately equals to, it has to be less than, sorry, I have the wrong way, greater than or equal to this value. You cannot round down. You can round up by more than 30 now. Okay, all right, you can make that even 35. Next, you have to choose where does your frequency distribution start? It can start at the minimum, and it can start before the minimum, but it definitely can't start after the minimum, right? Because then the minimum would not be placed in the class. So you want to start somewhere to the left of the minimum. You don't want to start too far to the left, right? Because you start way to the left, right? To do your classes, you might not make it to the max, right? So the more your class width is bigger than this number on the right hand side, the more flexibility you have in choosing what your first lower class limit. Now you have your lower class limit and the class widths, right? The next part is easy. Using the first lower class limit and the class width, you can find all the other low limits, right? By just adding the class width repeatedly until you're done. Then it's easy to determine the upper class limits, right? Then you put those in a column over here, and then you just do the easy part, counting the number of data values in each category. Now I'm giving you the steps here, but it's hard to see without actually going through this procedure, right? So I'm going to do an example, but I want you guys to have enough time to write this down, sketch it out, right? You can write down the whole thing. The slide will be on there, but roughly select number of classes, calculate class width, find your first lower class limit, find the rest of them,
then use that to create your table. I will show an example of doing this. But are there any questions based on this procedure in of itself? It's okay if you don't quite follow it, right? Because it will be easier once you see an example. So they made the frequency distribution, right? This is the same data. So they gave us the table, but let's figure out how they started that, right? So let's see those of you who have it. The first step is to do what when you're making frequency? How many classes, right? And they say do 5 to 20. 20 is a lot for us, we're doing an example that fits both the class period, so I chose how many? 5. 5. It's a lot less categorized, right? So I chose 5. There's not a right or wrong. Well, there are right and wrong answers, but there's not one right answer, and there's some ambiguity. So on a celebration, I might, if I ask you to do this procedure by hand, I might tell you how many classes to use. So I'm choosing 5 classes. So now that I've chosen 5 classes, my second step is to do what? The width, right? So to do the width, the formula we want to use is max. Might be a little bright. Let me change colors. Minus min divided by number of classes. Right, that divides how far do these classes need to reach, right? And then how do I divide that up into the appropriate number? So it's easy to look, right? What I kind of do is I look for a large value and then see if I find something bigger on there, right? So, okay, I see 255 is a pretty big value compared to the other ones. Does anyone see a bigger value on there than 255? Yeah. 308. Does anyone see a value bigger than 308? No, that is the maximum, right? Sometimes you just have to search. Anyone see what the minimum here is? Yeah. But Manuel, you see it? 83 is correct. Number of classes, of course, we decided was 5. Okay, when I do this, I get 225. Divide that by 5, you end up getting 45, right? So that is our minimum value for a class, right? You can do 45. You can add the whole number. It's not terrible, right? It's not 43. It's not 41. But you want to make it even. But if you did 45, you would have to start exactly at the 83, right? That's not a convenient start. So to give us some leeway, let's increase this 45 to a very round number that's near 45, but larger. That would be 50. If you chose 45, right, and you chose an appropriate minimum, I wouldn't take off. So there is, right, some leeway here. There's not exactly one correct way to do this. So I'm going to choose 50. Now that I've chosen my class, yes. You wouldn't be able to get lower because, right, the difference between the smallest and largest value is 225. Right? So our smallest class, our largest class has to bring that. If I ran it down to 40, okay, it's back to 40. 40 times 5 is 200, right? But, okay, I started exactly at the minimum, go up 200. I got something outside of the minimum. I can do that, and I would end up creating a smaller, right? Or I can have to add some class.
Now, if you do this, you can change number five. Set it for mine a five, or you struck to say five, you can't do it. Like, that makes sense. That's what I'm saying. So you can do that, but then you just have to decide, okay, I'm adding more classes. All right, so after we choose our class width, we then have to do what for step number 3? I wrote it down. Yeah, so we choose the first lower class boundary, right? We have to choose where our table starts. Now, again, we want to start around our minimum, but we cannot start greater than our minimum, right? Because again, right? But right, that is happening outside of our first class, grade class, right? So our minimum is 83. This gives us more flexibility, right? You can try this when you mess around. So our min is 83. If we chose 45 as our class width, right? If you go exact, I would have to start exactly at 83, right? And that would be tough. So I don't want to do that, right? But now I have, making it this much bigger means I have some more flexibility. So instead of choosing 83, I could start at 80. Or I could even do 75. I'm going to do 75 just because 75 is exactly 1.5 times 50, right? Which is kind of what we were looking at here. But and because that's what they did in the textbook. But there's no particular reason why you couldn't have started at 80. I might even be natural for you. Would anyone have started at 80 if I gave this exercise without telling them? Yeah, you might have. That's totally fine, right? Or start at 80, that is good with me, but we're just going to choose to do 75. Once you have the first class boundary, you can easily find the other class boundaries. So let's start with the lower class boundaries. So the first one we decided was going to be 75. Right? The next one then would be, well, the class width is 50. So the next one, everybody would be 125, right? Because the width is 50, right? So the next boundary, right, one class over would be 75 plus 50, 125. And you can know to stop doing this when I have 5, right? Because that is how many classes I have, right? You want to create the table, but to help you do that, also be good to have your upper class boundaries. So, and that's just going to be easy to find once you look at. So it's going to be one less than your previous class boundary, right? So my second class starts at 125, so my first class must end at 124. This one starts at 175. The previous one ends at 174. And you can do this one, okay, based on the rate that I'm doing it, right? It's going to be cabinets, right? 20. Okay, now when you have that, this is the easy part. Although it is quite tedious, right? So all we did right now is create the categories. Then you actually have to place the numbers in the category, which is pretty simple, although it can be tedious. 107, all right, that goes in the first category. 139, all right, second.
That one goes in the third. In the third as well. This one goes in the last one. This one goes here. This one goes. You see how I'm doing this, right? I'm just assigning them. This would take a while. I don't think it's very illustrative to your learning, but once we finish that, we would get to this table right here. Sorry that I wrote over it. I keep doing that, right? You know, you don't have to worry about the same thing that I gave. Examples in your text, right? So. Not a bad place. Any questions on what I did? Okay, so if you have no questions, some other things, and then we'll get into histograms and whatnot. Okay, so when you look at distributions, right, you can have the most common distribution of now the word normal here means a specific kind of distribution. This is the most common, and it's called, hey, that's but that doesn't mean it's anything that's not unequal. Frequencies start low, increase to a couple of high frequencies, and then decrease, right? So if you think about it, and it should also be roughly symmetric. So it should increase, then decrease, right? And it should do so in a symmetric manner, right? So the frequencies we had here do part of it. It increases to a maximum and then decreases, but it's not symmetric, right? Does everyone see that it's not symmetric? So it kind of fulfills the first rule of normal distribution, but not the second one, right? So here's one that is completely normal, right? So if there were two people that had a waiting time of 75 to 124, and A for 125, 7 to 174, then all 30 had, right, in this time, then it would take them 2 again. This would be considered a normal distribution, right? It doesn't have to be exactly this, right? For 29, like 9, right? It doesn't have to be perfect, right? The normal distribution, right? The one you see in a textbook is, of course, going to be perfectly symmetric, but right? Things that should be symmetric by chance might not be exactly symmetric. So you still say, okay, that's normal, even though it's not perfect, right? That's one type of distribution. Gaps, right? Gaps can show things are that data comes from two different populations, right? So here's a way you can think of it, right? Suppose I went to let's see here. They have this children's show, Peppa Pig, right? So let's say I'm looking at the distribution of, and there's a theme park in Britain called Peppa Pig World, right? What are the ages of people that are there? I doubt a lot of people in this class would have an interest of going there, right? So who are you going to find at that? You're going to find small children and their dolls. What are the dolls doing there? Their parents, right? Not right. If I don't have kids, if I'm there, people are going to be like, "Sir, what are you doing here? Well, I need to talk to this police officer over here." I don't know, right? They're just going to check. So imagine the frequency distribution there, right? You might have 0 to 5, 10, 6 to 10, 5, right? And then you might have 30 to 35, right? And in between 10 and 30, there might be nobody, right? So makes sense, right? So if you have, you're looking at one group, people at the right? But there are really two populations there, children and their parents, right? So you would see kind of two peaks, right? Two large values in the gap, but it's like almost nothing
right? Literally nothing or very big, right? So that shows that the data came from two populations, right? Kids and that's contained or something like that. Now the converse isn't necessarily true. You could have two populations, right? Of girls, Asian, that's whether they're right? So presence gap can show that the data from populations, two populations, doesn't necessarily mean them, right? In some cases, it's obvious. We get what's going on, right? When I said this age gap for people at a, children's theme Peppa Pig world, but it's not always obvious. Anyone here collect coins? I have not gotten one from my other period either. I guess you do a little bit. Yeah, that's okay. And a lot of people in their teens and 20s aren't excited about coins because we've got more exciting parties. All the dancing. I don't know. It's been a while since I've been in college. I don't remember what you guys did. Okay. What do you notice? Maybe you know about this, right? What do you notice about these are the weights of pennies? Obviously, these are my units. Yeah. What do you notice kind of strange about this thing? What? No middle. There's a big gap, right? This one might be confusing. We're not like appearance from children, right? Things, right? So you might be thinking about, are there two different populations? And this may have not, this would be unlikely for if you put a bunch of pennies now, but if you go to your grandparents' home, right? Some of your grandparents might have a giant jar of coins, right? They've been saving loose change for the last 20 years and have not bothered to organize it. Does anyone have a giant bottle full of loose change somewhere in their home or know a family member who does? Like, yeah. I did that once and I started organizing it because it ended up being that there was like $40. Right? It's just too much. So older ones, you might see this. Anyone wonder, right? This is the it actually is two populations, but they're all pennies. Does anyone know what? Can anyone think about what the story might be here? Yeah, that's true. That's true, but but some would be, but like in this case, either the penny is leading, dirty, right? There's no that doesn't quite make sense, right? That would be very large gap. Yeah. That'll that I don't know which one is that makes sense. What happened is, not everyone knows this. They always tell you pennies are made out of everybody in one word. You're wrong. So that used to be the case before even I was born, right? So for right 83 up until 83, right? So this is something that just kind of sticks out there, right? They made pennies 95% copper, 5% zinc, right? But what you could buy, right? I don't know if you have parents who've all been experiencing inflation, but your grandparents might be like, I could buy a loaf of bread for a nickel when I was your age, right? Inflation, the bargaining power of the penny decreased, right? And it ended up costing more than 1 cent to make. That's not a good way to do it. So they changed the metal composition after 83. Now, we don't people five at the top. So we can really think about things. Having some confidence that we get out of game, right? So, I don't know. That's I have no idea. So, this is clearly one of the settings, right? So, yeah, right. If we just look at now, the problem is most of you can see some are really dirty, some are really clean, right? Probably so you're more likely to get something like normal distribution, right? So, but when you have some big gaps, you want to think of is there something? Am I really looking at two different distributions that somehow have gotten fused together, right? And when gentleman back, I can't see. Point collecting definitely changes that, right? So gaps can suggest to population, right? Another one, I could have made a more obvious one, right? If I just did points Burgundy, yeah, you can score two separate, right? You said I missed 10 points overall. I don't have a lot of it, right? I have 3 times, right? If I just wait they definitely do not have. You have a lot of gaps, like you have gaps between dimes and pennies and nickels, nickels and quarters. Questions here about which gaps can show? Okay. Relative frequency distribution is very similar to a frequency distribution, except giving counts of units to percent, right? Or you could do it as decimal fraction, right? So there's two different relative frequency distributions. One for waiting time at McDonald's, one for waiting time at Dunkin' Donuts. That should be a mistake. The percent of these should always add to it. Great action. Sometimes you might not make a mistake, they might not add up. Drink one. These three numbers add up to 100%. But let's say around years percent, all three are going to be brown. Occasionally, they might add up to very slightly less than 100% because of this phenomenon, right? But they should almost always add up to 100%. They should never add up to more, and if it's less, it should just be very, very slightly less. Now, percentages can be useful because they allow you to compare. Suppose I have 100 cars at McDonald's, 150 at Dunkin' Donuts, right? I can't really compare how many are in each category because one of them, there's just more overall, right? But if the percentages, then I can say, all right, it looks like that usually it takes less time at Dunkin' Donuts, right? So frequency distribution counts, relative frequency distribution percentages. Then there's the third type. I need this too much. It's called a cumulative, word I always have trouble saying, frequency distribution, where notice instead of before, right, these are non-overlapping classes, right? Here, notice these classes overlap, right? It's 35, right? At 35 less than 175, right? That includes, right? It's 45, that's less than 225. That includes this 35 and includes this 11, right? I know they add up, it's not they do that, right? Just think about successive circles, right? So how many trips people who visited McDonald's are represented in this cumulative frequency distribution? 50, right? It's just the last number. Because everybody was less than 325, you have some of those were less, right? So you can easily build your distribution by subtraction. Right? So if you want to get not a cumulative frequency distribution, just a regular frequency distribution, you can use subtraction, right? So this one's going to be the same. That's going to be 11, right? Okay, but to get this one, right? Okay, so 35 are less than 75, 175, but that includes this 11, right? So to get this, I would do 35 minus 11 to get me 24. Right? And then you would do that for each of these other ones. 45.
everyone kind of see the relationship here because, right, this how they're 48 less than 275. There are 50 here, so that difference is caused by the two that are in between that category, right? And that makes it easier because otherwise you might have to do a lot of subtracting, right? But you can just subtract the ones there. Okay. Questions on this type of distribution? So just think about the just describe before we start the next section to talk to your table mate. What are so there's three types of frequency distributions, just without a word before it, right? What are those? How is that different than the relative frequency distribution on the previous page? And then how is that different than the cumulative frequency distribution, right? And how can you transform between the types, right? Kind of showed a little bit about that. Does everyone understand what I'm asking you to talk about? All right, let's talk about that for maybe 1 minute, 2 minutes, and then we'll start the next section. All right, let's come together here. I'll take some questions, but I was overhearing, right? But the group of you were saying, and I don't think something was confused right now. Talk about a normal distribution. Right? For a normal distribution, right? So frequency distribution that I'm talking about, right, are different, right? We represent the same data, right, in a frequency, right? Number of classes. Relative to the percentage of these classes, or in this one, we don't have classes. A normal distribution is the pattern you find part of the distribution, right? So that distinction might be a little bit confusing, but I think the next part of this lesson will help you kind of figure that out. We'll talk about histograms and the patterns we see. So right now, other than the gaps and the normal thing, those are patterns you might see inside of the distributions, right? But here we're just talking about how do you change data, right? And how do you represent it in a table, aka a frequency distribution, right? Does that kind of clear that up? We're going to spend most of the next section talking about what sort of patterns you might find and a little bit about their significance. Okay, so section 2.2